When an astronaut seals their helmet and clicks the suit's locking ring into place, they complete just one of thousands of mandatory checks. This exhaustive routine exists because aerospace engineering operates without a safety net. Out there, the margin for error is absolute zero, and the environment is entirely hostile to human biology. The dense technical manuals dictating these procedures were written in blood, built line by line from the data recovered from the wreckage of fallen crews. To trace the path of how spaceflight became survivable, we have to look closely at the cascading mechanical failures and the human hubris that caused its most devastating tragedies. In April 1967, Soviet engineers identified over 200 technical defects in the new Soyuz 1 spacecraft, but the Kremlin demanded a launch to coincide with a May Day propaganda event. Veteran cosmonaut Vladimir Komarov boarded the defective ship anyway, knowing that if he refused, his backup, his close friend Yuri Gagarin, would be sent to die in his place. This schematic illustrates the mechanical consequence of ignoring those design flaws. During re-entry, the main parachute container failed to open correctly, leaving the primary canopy hopelessly tangled. When Komarov deployed the backup chute, its lines immediately wrapped around the snagged main canopy, providing zero drag as the capsule struck the ground at 250 miles per hour. 19 years later, a similar pattern of ignored warnings doomed 7 astronauts aboard the Space Shuttle Challenger. The night before launch, engineers at Morton Thickle desperately warned NASA management that the 18-degree Fahrenheit weather would cause critical seals to fail. Under intense pressure to avoid another delay, NASA management overruled them. This diagram shows exactly what happened 59 seconds into flight. The cold-stiffened rubber O-rings in the right solid rocket booster failed to expand. This allowed a jet of 5,000-degree Fahrenheit gas to escape from the side of the motor. This escaped gas acted like a blowtorch. It sliced through the strut connecting the booster to the external fuel tank. At 72 seconds, the compromised tank ruptured, violently mixing thousands of gallons of liquid hydrogen and oxygen in the sky. Physics does not negotiate with launch schedules or public relations. The loss of both Soyuz 1 and Challenger forced multi-year halts to their respective programs, proving that political pressure cannot override engineering reality. In 2003, during the launch of Space Shuttle Columbia, a 1.67-pound piece of foam insulation broke away, falling from the bipod ramp area of the orange external fuel tank. At 81 seconds after liftoff, traveling over 1,500 miles per hour, that piece of foam struck the shuttle's left wing. Foam strikes had occurred on previous missions without incident, leading managers to believe the debris was a routine annoyance. When a debris assessment team requested high-resolution images from military satellites to check the wing for damage, ultimately, NASA management explicitly denied their urgent request. This heat map diagram illustrates the physics of Columbia's re-entry over Texas. The foam impact had punched a hole 6 to 10 inches wide in the reinforced carbon panels on the wing's leading edge. As the shuttle descended, 2,500-degree atmospheric plasma flooded into the breach, melting the wing's internal aluminum framework from the inside out until it completely separated from the fuselage. A different kind of unseen failure struck the Soviet Union's Soyuz 11 crew in 1971. The 3 cosmonauts had just completed a record-breaking mission. Because the spacecraft was considered safe, the men wore only soft communication caps and fabric flight suits for the journey home, rather than pressurized gear. As the orbital and service modules jettisoned, a piece of pyrotechnic debris from the explosive bolts damaged a single pressure equalization valve. While the craft was still 550,000 feet high, the valve opened, venting the entire cabin atmosphere out into the freezing vacuum of space in exactly 112 seconds. These silent failures forced permanent industry changes. Columbia's loss led to mandatory in-orbit inspections of the thermal protection system, while the Soyuz 11 tragedy established the strict requirement that crews wear full pressure suits during all dynamic phases of flight. In November 1967, test pilot Michael J. Adams climbed into the X-15 to face the inherent peril of the unknown. This mission lacked the political pressure of the Soyuz or shuttle programs. Here, the enemy was the extreme physics of the literal boundary of space. As Adams reached an altitude of 266,000 feet, the aircraft's reaction control system malfunctioned. in the near vacuum of the upper atmosphere, there was almost no aerodynamic feedback. Without sufficient air pressing against the control surfaces, a slow, inadvertent yaw motion developed, completely masked from the pilot until it was too late. This telemetry visualization maps out the X-15's final descent. Adams was entering the denser air at 65,000 feet, traveling sideways at Mach 3.5. Hitting the thick atmosphere at that extreme angle of attack triggered a hypersonic spin, subjecting the aircraft and pilot to violent loads exceeding 15 Gs, instantly tearing the fuselage apart. Adams's death drove an immediate overhaul of backup attitude control systems and established new parameters for high-altitude pilot training, directly feeding into the design of the spacecraft that followed him. Every tangled parachute, frozen O-ring, and shattered piece of foam strike is embedded in the technical foundations of modern aerospace engineering. Today, when a multi-million-dollar launch is scrubbed for a minor temperature drop, or when astronauts spend hours meticulously scanning heat tiles with a robotic arm in orbit, they are directly executing the legacy of Komarov, Adams, and the crews of Challenger, Columbia, and Soyuz 11. Spaceflight will never be entirely safe. The hostile vacuum of the cosmos offers no leniency, but the ultimate threat to any crew remains human complacency. The moment humanity stops rigorously respecting the extreme dangers of orbital mechanics and thermodynamics, the universe will remind us, and the toll it extracts is always devastating.